number A, and then let A go to infinity. So take the antiderivative of 1 over x, which is ln A, ln x. Evaluate it at A, evaluate it at 1, subtract, and then take the limit. So this is ln A minus ln 1. And now on that function of A, you will let A go to infinity. As A goes to infinity, ln A goes to a ln of a large number, and ln of a large number goes to infinity. That is to say, as x goes to infinity, ln x goes to infinity. That is to say, if you graph the log of a function, ln x, and you let x go to infinity, ln x goes to infinity. What is this? This is a divergent. Divergent. Another very important one. Very important. Okay, now, with the first type of improper integrals, you will have a definite integral up to some number A. And that involves an antiderivative. And you are all experts at finding antiderivatives. It may involve U substitution. It may involve integration by parts. It may involve trig substitution. It may involve
Partial fraction.
indeed. Let's do another one. Let's take a look at this. Let's say you want to integrate from 1 to infinity, x e to the minus x dx. Improper integral. And we want to know, well, if you grab this thing, I have no idea what it looks like, but I think it's something like this. Monash calculus 1, for example, experts at curve sketching using derivatives and local maximum, increasing, decreasing, concave up, concave down, and nonsense. Or just buy yourself one of those fancy calculators. Now the question is this area here finite? That is to say, does this function go to 0 quickly? If it does not go to 0 quickly, you're not going to get a finite number. Now, observe that x is going to infinity, and this is going to infinity, and this is going to 0. So there's some battle going on. You see? Suddenly in this region here, this guy's winning. And then they say, okay, I'll call it a draw here. And then this guy says, bye-bye. Now the question is, who's winning? The fact that this is going to infinity fast, or this is going to 0 fast? And the answer is this guy is going to 0 too fast, exponentially fast. He's going to make this area, in fact, finite. All right? So we're going to do this as an improper integral. We will say, take the limit as a goes to infinity and integrate up to a. Now I need the antiderivative. How do I find the antiderivative of this thing?
U sub.
No. Huh? Integration by parts. So now I'm going to take another piece of paper and do my multi-step problem now. I'm going to find the antiderivative. And I'm going to do the integration by parts in my head because you're all experts in that. If you don't know what I do, go home and review your integration by parts. I'm just going to find the antiderivative. So I want to differentiate this out. Huh? So I'll call that dv. And this I will call dv. The integration by parts formula says equal to uv minus the integral of v du. We'll use x. V is the integral. What's the integral of e to the minus x? Negative e to the minus x. Negative e to the minus x. What did we say v was? Negative e to the minus x. And u is x. What is du by dx? So what is du?
Or
Du by dx is 1, so du is dx. Come on. Minus e to the minus x dx. Okay, that's a nice quick review of your integration by parts. So here's the antiderivative. What is this? Minus x e to the minus x, and then this is just plus e to the minus x dx. What's the antiderivative of e to the minus x?
you mean
E to the
negative e
minus
minus
x.
x?
So now I lose that here. Right? You have the antiderivative. If you don't understand this, go home and do your integration by parts. So we are going to take the antiderivative, minus x e to the minus x, minus e to the minus x, evaluated at a, evaluated at 1, subtract, and then let a go to infinity. Now forget that now. Here. Let's use the antiderivative. Go home and check it. You get the antiderivative. So I'm going to put a. I'm going to put 1 and subtract, and then let a go to infinity. Okay, let's put the a here. What do we get? Negative a e to the minus a. We're not taking the limit yet. We're getting a function of a. Minus
E to the negative a.
minus e to the minus a. And now we're going to put the 1 in there. What do we get?
1. Negative 1.
Negative 1 e to the minus 1 minus
E to the negative
e to the minus 1. Now this is clearly a function of a. And we want to take in that limit, in that function, we want to let a go to infinity. Huh? We want to let a go to infinity. Now this is just go, as a goes to infinity, this is going to be what?
2 e. Or 2 e to the negative 1.
Negative 1 e to the negative 1 minus negative 2 e to the negative 1. So we don't have to worry about this. But this guy here, what is that guy? The limit as a approaches infinity of minus a e to the negative a minus e to the negative a. Well, what's this one as a goes to infinity?
0.
Indeed, 0. What's this one? Well, the question is who's quicker? Does this guy go to 0 to infinity faster than this guy goes to 0? We did this last time. That is to say, what is the limit as x goes to infinity of x e to the minus x?
E to the x wins.
Take a look at your notes.
Exponential.
We did this house. How did we do this limit last time?
L'Hopital's.
Indeed. What did we get?
We got that.
Oh, we did it like this one. Limit as x goes to infinity of x e to the minus x.
Yes.
Of e to the x. What did we get?
1 over e to the x.
1 over e to the x, and x goes to infinity.
0.
So this is? And this is?
0.
This is?
Negative e to the negative
2 e to the negative 1. Okay, you try it. Now you have to know how to find antiderivatives. You have to know how to find antiderivatives. And if you don't know how to take limits, then you use L'Hopital's rule. So we derivate that, you get 1 derivative that, you can use the x, that x goes to infinity. Okay, you try this one. infinite line. So first you have to find the antiderivative. Evaluate it at 6, evaluate it at 8, and then let A go to infinity. Last time I didn't use A, I used M, is that correct? Not a big deal. What did I use last time?
Use M.
Yeah. Yeah, M A. That is-